live with it. Alright, so E is this and F is this. And now let's compute, okay, let's compute the measure of, okay, E actually. Alright, let's compute the measure of E. Okay. What would be measure of E? By definition, it's going to be the Lebesgue measure of E intersection 0 to 1/2. We're doing something similar. It's not going to have measure 0. इसको new अगर दूँगी, ठीक है? और यहाँ मैं लिखूँ, okay, let's take 1/2 to 1. Is there anything going to be common? This will be the empty set. This will be the empty set. Enhancement as well. So compute nu of E, and what would be the mu of F by definition? So it's going to be the measure of F intersection 0 to 1/2. Okay? 0 to 1/2. And what is common in both? Huh? F is 1/2 and 0 to 1/2. So nothing is common, then this is empty set. ठीक है? So what we did? Let's quickly. So mu is the Lebesgue measure on 1/2, 0 to 1/2. So in other words, the measure of A is the Lebesgue measure of the sets intersect with the 0. So in other words, the part of A that falls here actually. And similarly, nu is the Lebesgue measure restricted to 1/2 to 1. And I'm saying that take E to be 0 to 1/2 and F to be 1/2 to 1. F is not an intermediate, yes. Then the measure, mu of E is going to be the measure of E intersection 1/2 to 1. So E is 0 to 1/2 and this is 1/2 to 1, so this must be empty set, so this must have a 0 measure. And similarly, mu of F is, what do you call it? F intersection 0 to 1/2, and F is 1/2 to 1 to 0 to 1/2, and it's again empty. So, we have is actually, that's it. That's an example. So there's another example you can go through it for yourself if you wish. Because I think this is a simple example of a measure being similar to another measure. Now let's do this final result and end up this chapter and we'll break afterwards. The final result is called the Jordan decomposition theorem. Final result is Jordan theorem says that if mu is a signed measure, mu is signed measure, measure a space X to A, then there exist positive measures, both are positive measures, mu plus and mu minus, whether there exist unique positive measures, okay, mu plus and mu minus. I'm sorry? This pair is unique, okay, such that mu is mutually singular to mu. So mu is singular to mu, plus mu is singular to minus mu, and mu can be written as mu plus minus mu minus. Okay. So what does this result is telling you? Telling you that if you have a signed measure, then you can break it down to the positive and negative form. So you can find a mutually singular positive measure such that mu can be decomposed as the difference of two positive measures. Okay. Now, one thing that you can conclude from this result also is that why it is sufficient to study the positive measures. Why it is sufficient to study the positive measures? Why? Because if you have a signed measure, you can always break it down to the positive measures. Okay? So, signed measures are good. Positive measures. So, theory of positive measure is
exactly said as we did in convergence.
It's not exactly the same because you have this additional condition. So you can always find two positive measures with these two properties. In other words, you can always break a signed measure into decompose it into the difference of two positive measures. And this is something basically shows that positive measures are important, and it's important to sufficient to basically study them. I'm proving it because I'm going to use it in one of our results. So let's prove it. Existence is easy. It is extremely easy. The only thing that we have to struggle and work on is uniqueness. Uniqueness is going to be a part. So, if mu is a signed measure, if let mu be a signed measure, okay, then the previous result that we proved showed that you can find a positive and negative sets. Okay, so from Hahn decomposition theorem, so there exist positive set, positive set E and negative set F such that they have nothing in common and the union of the both union of both of them. Now observe this. So consider the mu of A. A is an arbitrary, measurable set. Obviously, I can write this as A intersection X. Okay? And obviously, I can break it down to the two parts. So one part that is common with A intersection E union A intersection F. So one part that is common with F and other part that is common with EF. Okay? So this is same as mu of A intersection E plus mu of A intersection F. We are happy with it? Okay. Give this guy, now define. Now since the measure of a set can be broken down to the measure of positive part of it plus the measure of negative part of it. Okay. So let me define mu plus of A as the positive part of the term. Okay? And let me define mu minus of A as, have a guess,
A intersection
minus A intersection. Okay? Because if this would be the case, we are done with what we call the existence result, because this is same as saying that mu of A is same as mu plus of A minus mu minus of A. Okay. That is mu at the map is same as this difference. Okay. Resistance is pretty straightforward. So let's prove uniqueness. Okay. And in order to show uniqueness, what do you need to show? You need to show that, imagine you have another decomposition for the mu. So let mu plus and mu minus, okay, is another the measures such that mu plus is singular to mu minus, and mu can be written as mu plus minus mu minus. Okay. So my task is to, my claim is to show that mu plus is same as mu plus and mu minus is same as mu minus. Now, by the way, so now since mu plus and is similar to mu minus, so the definition tells me that I can find two sets E and F which are disjoint, not necessarily negative and positive. I can find two sets which are disjoint and whose union is exact, such that one of them is 0 under one measure and another is 0 under other measure. So by definition, I would say there exists, I can find, okay, E prime and F prime such that what? There exists E prime such that mu plus of E prime is 0. Okay? And mu minus of E prime complement, whatever this complement F is going to be this. Okay? Set F prime as mu prime complement. Agree? So thus I have E and F, but F I want to recognize it as in the terms of E prime because their their intersection is empty, so F prime must be the E prime complement. I have no other choice. So thus E prime is 0 under mu plus and E prime complement are F prime is 0 under mu prime.
That will be the reason for the zero time.
So here's the thing. So we say that since mu plus is singular to mu minus, so by definition I can find two sets, okay, E and F, such that one is 0 under one measure and another is 0 under the other. Other way around, but and obviously if you take E prime intersection F prime, it's empty, then their union is X actually. Now let's begin by observing. So here's the one thing, don't confuse E and F being positive and negatives unless there is a B. Okay? But at the moment the E and F are any sets. Okay? You don't necessarily have this structure. So let's see that what we can conclude about it. So take any subset A to be F prime. Okay? Take any subset A of F prime. Then I would say that mu minus of A is less than or equal to mu minus of F prime, but this is 0. This is 0. And if this is 0, so what's it now? By the way, so mu minus of A must be 0. Isn't it? Think about it, because mu minus is a positive measure. It's a positive measure. So why? Because the statement of the theorem is saying that, okay, for every signed measure you can find unique positive measures. They are positive measures. So obviously if mu minus is, the measure of mu minus is less than or equal to 0, it's obviously bigger than or equal to 0, so this must be 0. And so what we can conclude from it, that if I have a mu of A, okay, and since mu of A is equal to mu plus of A minus mu minus of A, since this is same as mu plus of A minus mu minus of A, so this must be equal to mu plus of A entirely. So if you take A to be a subset of it, then you get mu plus of A. Okay? By the way, what does then happen if that this is a non-negative set? Okay, because mu plus is a positive measure. So this must be non-negative. So what I did, I took an arbitrary subset of F prime and showed that its measure is a non-negative. So what does it mean? Hence F prime is positive. So it's a positive set. Okay, positive set under mu in the context of mu. Okay? So previously we didn't knew that, But now we can decisively say that E prime is a positive set. And if F prime is a positive set, then obviously E prime is a negative set. Actually, we can make it. So similarly, so obviously we can verify E prime is a negative set. Agree? So, since mu is a signed measure, keep track of the things that we are doing. So, since mu is a signed measure, so I have a positive and negative set by decomposition theorem, previous decomposition theorem. Now, interestingly, I have found another positive and negative set, E prime and F prime, such that they are disjoint and their union is X actually. Okay? So their union is X. So we know that they are symmetric. So the symmetric difference also from again decomposition theorem part 2, symmetric difference of E and E prime is equal to the symmetric difference of F and F prime, and this symmetric difference is a null set. Okay? So I can run this argument. Okay? So I would say E prime and F prime is another Hahn decomposition. So let's give it a name, Hahn decomposition of X. Okay? So what we can conclude is that E symmetric difference E prime is same as by uniqueness. F symmetric difference F prime is a null set by the last layer. Okay? So we are almost done. Obviously with respect to mu. Okay? Always keep track of a thing that the things that you are, because at the moment there are 5 measures involved actually. So you have a mu and a nu and a, you have lots and lots. So you have to keep in track that what measure you are talking about. So it's a null set, but with respect to our key measure mu that we are interested in. Now, another observation. What would be mu plus of E prime? We have already mentioned, so I don't need to write it. So let's directly jump and let's directly show the equality that mu plus is same as mu plus and mu minus is same as mu minus. So I'll show one and you can see. So to show the equality, I need to show that this nu plus and mu plus agree on all elements of the sigma-algebra A. So they agree as a map. Okay. So let's take any A, abstract A from sigma-algebra A. Okay. And let's compute the mu plus of A. Okay. So let's compute the mu plus of A. Can I say that the mu plus of A is same as mu plus of A intersection F prime? Okay. Mu of A by definition, huh? Mu plus of A. You have to be careful. Definition is something else. Definition says that I have mu plus of A is the mu of A intersection E. Okay, you have to be a bit careful.
But you get mu of A and mu of plus
I'm sorry?
A. Ram stop. Mu of A.
So A is a subset of,
F.
why is it a subset of F?
So you have mentioned
A is an arbitrary, element in sigma-algebra. So that means that, okay, so that means that A can be broken down to the A intersection F prime union A intersection E prime. Okay, that's computed in this way. So this means that mu plus of A intersection F prime plus mu plus of A intersection E prime. Okay? Can I say that mu plus of A intersection E prime is 0?
E prime is subset.
Because it's a subset of E prime and we know that mu plus of E prime is 0. Okay, so mu plus of A intersection E prime must also be 0. Hence I would say that this is same as mu plus of A intersection F prime. Agreed? ठीक है? Let's conclude. What I showed that mu plus of A is same as mu plus of A intersection F prime. Okay? By the way, what would be mu minus of A intersection F prime? Maybe just do rough time. What would be the mu minus of A intersection F prime?
Minus of
Will I have a conclusion?
mu minus of F prime is 0 and mu minus of A intersection F prime is less.
Mu minus of A prime.
It is 0.
Is
Mu,
it less
okay.
than?
So this must be 0.
This is 0 and this is less.
So this must be 0. No? So this means that I can write this as mu plus of A intersection F prime minus mu plus of A intersection F prime, right? So this is same as mu of A intersection F prime. But I know that mu has another decomposition. This is same as mu plus of A intersection F prime minus mu minus of A intersection F prime.
दोनों positive है?
This is 0. So if I am subtracting 0, it's not making any difference.
Minus close to
So
minus.
yeah, दोनों are
Mu of
positive.
minus.
Minus mu minus.
So yes, this must be negative. Yes. Okay. So now what we can say? Can I say that this mu, so A intersection F prime is same as A intersection F, mu minus of A intersection F, isn't it? So if the symmetric difference